So welcome to, as I said, KIOSC. My name's Kat. I'm going to be taking you through Unit 4 Organic Chemistry. So this is mainly for your teachers, but that's okay because it's good to know all the dot points that you'll be looking at when we're going through this program. And another good thing to know is what we're actually aiming to do by the end of this program. So the first thing is we want to be able to interpret infrared, proton and carbon-13 NMR spectrums, to use those spectrums to analyse and determine the structure of an unknown sample. And from there, the last one, which is pretty cool, we actually got our HPLC machine all up and running, and Etienne is our guru with that, so he'll be helping us, to be able to construct a calibration curve and determine the concentration of an organic compound using that calibration curve. Now, before we get started completely, if you have a ruler or graph paper, that would be fantastic because you are going to be drawing a graph today. So if you have that, could you raise your hand to say, yeah, I've got some graph paper so I can do this on? Worst case scenario, you can do an Excel spreadsheet, but that's a bit cheating. It's probably better if we draw it by hand. So can you raise your hand if you have access to graph paper to draw your graph later on? Probably no one does any day.
That's right, we've got 3 if we do.
That's okay. If you don't, that's fine. We can get around it with a ruler and pen. So, as you'll see, we've got our program overview here. Most of you have already done the overview of the analytic techniques or organic analytical techniques. You've done your pre-work, which is actually past papers. So past questions, sorry, I should say, which is fantastic because we're exposing you to more content and getting you used to the way the VCAA actually do their exams. What we're doing today is we're going to be analysing an unknown compound using infrared, our NMR, and then you're going to determine your unknown concentrations using HPLC. Who can tell me what IR stands for? Can anyone tell me what it means? You can put your mic on or raise your hand and let us know if you think you know what it means, or put it in the comment.
Got infrared spectroscopy.
Very nice, well done. What about NMR? Does anyone know what that actually stands for? Or is it just a bunch of letters that scientists have created? What do we got there?
Someone said nuclear magnetic resonance.
Beautiful. And the last one, who can tell me what HPLC stands for? And there are 2 answers with this one. Let's see if you can get both of them.
Chris has said high performance liquid chromatography.
Yeah, that's one of them. So high performance, what's the other one? We just changed that P.
Penola.
All close. Starts with P. Pressure, well done. High performance liquid chromatography, awesome work. And then once I leave you guys, you've got some post work to do. You have some more unknowns, which are 3 unknown different compounds, and you can go through using spectras to work out what they are. They're a lot easier than the one we're going to be doing today, but that's okay. And then you've got your post-work quiz. And once again, past exam questions, which is fantastic, more exposure for you guys. And then you've got your post-program survey, which helps us as teachers to see that we are meeting the needs for you guys and checking that, yes, you are getting some benefit or some things that we can change in our program later. So let's get started. So we have our case study here, and we have patient X was found unconscious and unresponsive on the bedroom floor. And when the ambulance officer came in, they found a black liquid in a cup beside them. They poured that into a container so they could use it in hospital later on to analyse and work out what it actually was and to determine if it's also in their system. How they were able to do that once they were taken to the hospital by ambulance, they were able to collect a urine sample over a 24-hour period, and they were able to get 3 litres. The other interesting part here, which is really important to diagnose these types of things, is their partner was able to tell us, or the ambulance officer in the hospital, that they had the following symptoms. They had anxiety, insomnia, which is having trouble sleeping, high blood pressure, rapid heart rate, and increased urination. So you guys are all going to be my organic chemists. And what I want you to do is analyse the spectras that we've printed out to determine what our unknown compound is. The other part we need to do is work out if it's in both our urine sample and the black liquid. Now, before we continue, you are going to be needing to log on to Canvas. If you haven't already logged on to Canvas in a separate tab, please do so now. If you're logged in, just raise your hand so we know that you are ready to go for the next part. And if anyone's having any troubles logging onto Canvas, just type it in the comments and we'll be able to help you out. Have we got everyone?
We've got about half. So Canvas is also called KIOSC infrastructure.
Yep. So the LMS or KIOSC infrastructure. Does anyone need the link to get to there? Can you chuck it up? Ta. You're racing to each other.
I'll let you get it.
So if anyone's having any problems with Canvas, just type in the comments and Etienne will be able to help you.
That's the one. Thanks, Dip.
How many more we got?
We have 7 more to log on.
Okay, so raise your hand if you're logged on. Type to us so we can help you if you're not.
Oh, 3 more to go. So we got Valentina, Hamna, and Taha. And once they're on, we've got everyone on.
Awesome, because we don't want to leave anyone behind. Two to go.
Yeah, one of them is confirmed by message.
Awesome.
Waiting on Valentina. I'm saying that name right.
So either type in the comments that you have access or raise your hand. If you're having any problems, just type to us and we can help you out. Okay, so now let's start. So the first thing we're going to look at is our microanalysis. And if this was in a lab, you'd be using your mass spectrometer, but that's been removed from the course this year, so that's okay. We can deal with it, but next year it will be back in. What we've been able to find is that when it was run through, there was a compound found in both in the black liquid and the urine sample from patient X. So we know from this that the unknown compound contains 49.18% of carbon, 5.39% of hydrogen, 28.65% of nitrogen, and 16.68% of oxygen. And this is done by mass, so it's mass percentage. The other part that they found was that they experimentally determined the molar mass to be 196 grams per mole. So in your shell, what you need to do in the first quiz called microanalysis quiz is calculate your empirical formula and your molecular formula. Now, I am being evil here because we need you guys to type out your step-by-step of your workings. So you need to make sure you show all your calculations. So have a go, guys. I'm going to give you about 2 to 5 minutes, and when you're done, just raise your hand. And when you get back, there'll be a poll waiting for you. If anyone's having any issues, just type in the comments and we'll be able to help you out. All right, guys, if you could all come back to collaborate. If you haven't answered the quiz yet or you're still working it, that's fine. You can go back to it later and fix it up. So as you see, I've got a poll there waiting for you. What I'd like you to do is answer which one you think is the correct empirical formula. So I'll give you 1 minute.
Yeah, there's only 4 that need to answer now.
Okay, just waiting on 4 of you to answer the poll for us. If you don't know the answer, that's fine, just have a guess.
Yeah, last.
Okay, 2 to go.
1 more. Yeah, I'm sure responses.
Okay, so now we've got the responses up there.
Yep.
So you've all done really well there, and I can tell you the answer is 3, so well done. So let's go through how we got that. So I like to do this as a table. That's just the way my head works. That's okay, we're all different. So the first thing, you set it out with your carbon. You then have your hydrogen, your nitrogen and your oxygen. Then you put your percentages in. Now remember, because it is percentage by mass, if you simply times it by 100, that gives you your mass in grams, which there you have across the top. Then from here you calculate your mole. So you're using your periodic table to get your molar masses. So let's focus on carbon. So we got 49.18, my apologies, and you divide it by 12. That then gives you your mole of 4.0938. And then once you've calculated the rest of them, you then do your ratio. So our smallest one, as you can see here, is oxygen, which gives us 1. Nitrogen gives us, rounding out to 2. Your hydrogen gives us 5, and your carbon gives us 4 in the end. Now, in regards to rounding up and rounding down, this depends. If it is a slight adjustment, that's okay. If you have a major roundup that you need to do, then you will need to go through and multiply each individual one. Then from here, we then put it into our formula, and you'll see, thank you, I'll hide it away. You'll see that it is C4H5N2, 1 oxygen. Now from here we can work out our molecular formula. So we've been given the molecular mass of 196 grams per mole. We now need to work out what our empirical formula's molecular mass is. And we simply do 4 times our carbon, 5 times our hydrogen, and that's incorrect, I'm going to have to change that. Can't handle that being incorrect. Let me just fix that one, you'll yell at me otherwise. 1 times our oxygen, not 2. And then we then put in our molecular masses, just like we did before. So 12, 1, 14 and 16. Then you multiply them and then you end up with 97 grams per mole. Now from here we do a ratio to work out if it's the same or if we need to multiply our empirical formula to get our molecular formula. So 196 divided by 97 gives us 2. So therefore we need to times our empirical formula by 2, which gives us our molecular formula of C8H10N4 and 2 oxygens. Now we're going to move to our infrared. Now with infrared, it basically gives us a bit of an overview or a snapshot of what functional groups are in our compound. At the top here, this here is straight out of your data booklet that you get from your VCAA exam. So I'm just going to jump into our video. So bear with me. Okay, so here is our infrared or FTIR machine. And the first thing you need to do before you run anything is do a background check. Then you load your sample. The really cool thing is you only need a tiny bit, so just like a couple drops. Once you're ready, you then select run and you end up with your spectro. Such a cool machine, just a benchtop machine. That was actually shot at our Hawthorn campus, so we're really fortunate. Normally our program would actually send you guys to Hawthorn. We'd send you guys to Hawthorn, but in our current climate we can't do that. Here is a really cool chart that shows you all the different organic functional groups, and there are a lot more here than you will actually need for VCE, but it gives you a snapshot of all of them out there. So it gives you a bit of an idea, and if you're unsure how it would look structurally, it helps you as well. And here's another chart showing you all the different wave number absorptions for infrared. Now, when we talk about this is to do with the bonds and how they bend and stretch. So depending on what they're bonded to and when you shoot the infrared at it, it does different things. So this here is our unknown spectra, and what I want you to do now is go through and identify any interesting peaks that you see. You'll notice here it's really busy here, so you won't be able to get too much from there. So what I want you to do now is go into Canvas. I'm going to give you 5 minutes to answer the quiz question there, and all you need to do is answer 2 questions and then jump back in here and you'll find a hole waiting for you. Okay, so well done everyone, you are correct. So let's go over these particular functional groups. So I've only focused on 3 here because, as I said at the start, that start section is quite busy, and luckily they're not mean in VCE to get you to answer what that would be because there's just too much going on. So this first one at 2,953 centimetres is the one that we asked the question for. It is your carbon to hydrogen bond. The next one is 1,693, and this is a carbon to carbon double bond. The last one at 1,644 is a carbon to oxygen double bond. And the interesting thing here, it is a amide, which helps us a lot because we know that we have nitrogens in our compound, which helps us to determine what structure we're going to have. So let's move on to our carbon-13 NMR. This allows us to determine basically what's happening with our compounds' different carbon environments. So the peaks that we see, they let us know what each carbon environment is represented like. The chemical shift lets us know what is bonded around those carbons to give it a different pull. And the last one is our no integration. Now with our proton NMR, we actually use this with the height to determine how hydrogens there are, but we don't do this for carbon. An interesting side note is that when there are no hydrogens, they generally have smaller peaks. So that's something to help us when we're deciphering what's going on. And over here, your table here is just out of your data booklet, just like the previous one for your infrared. Here is a bit of a chart with an overview of the chemical shifts. So it shows you where they start to sit depending on where the carbon is bonded to different groups. And the other thing I need to point out, which most of you already know, is that carbon-13 is not actually our normal standard that we're using when we find carbon. It is normally carbon-12. So there's only 1% of carbon-13. So it's really amazing. It's only in the last, I believe, 20 years or so they've been able to use carbon-13 for NMR. So jump out into our video here. And we're going to look at our benchtop NMR as it loads up, if it wants to. There we go. Okay, so this one's pretty cool. It's just a little one that sits on your bench. And the interesting thing with this, you have to do a process called shimming. And what this does is basically realigns your magnetic field before you put in your sample. So you have your tube there and it has a holder that it needs to sit in. So it gets placed into the top of the machine. And then what you need to go is to your computer. You then click your shim in the systems and it runs like a background check. It's sort of like calibrates. And then once you get a successful shim, you then can put your sample in. So now, just like we did with the infrared, you put in a couple drops, but this time you're putting it into the tube. It then gets put into a holder, and you need to make sure this holder's sitting at the right spot because you've got your magnetic field going through it. It then gets placed into the top, and then you run for your spectra. Now, this is really cool. You can have a proton or a carbon, and this particular one that they're running is a proton NMR. And you can see that you got splitting here. So let's jump back to our PowerPoint. Okay, and here is our carbon-13 NMR for our particular unknown. But we'll jump back to this one in a moment. We're going to go over our proton NMR first. Now this allows us to determine the proton chemical environments, just like you do for your carbon. And the number of peaks determines the number of proton environments you have. And the chemical shifts let you know what those particular protons are bonded near. And integration, the height of your peak actually determines how many hydrogens you have in that particular environment. The other part, which is really important, is your splitting, so your N+1. So if you were to have a hydrogen that has a carbon, then another hydrogen that has, there are two hydrogens sitting there, you would say that you have two neighbouring protons. So 2 + 1 gives us 3. You'll end up with a triplet. Once again, the table that you see on the side here is just from your data booklet. Here's another chart to help you if you want to see how those particular hydrogens bonded to other groups looks like. So it gives you an overview. The last part is at the bottom here. And as you can see, you can have peaks that are singlets, your doublets, triplets, and it just goes on and on. So what we'll do is jump back to that video. Okay, and as I was saying, this is a 400 megahertz NMR. It gets loaded in the top into our sample express, and it's a bit like a conveyor belt. So you can see there's a green light at the top here, and you push your start. You then need to go to your computer and you set up the spectra to run and be detected. If I could say that word, be good. From there, if we have a look back at our sample express, you'll see that it's moving around, and you'll see that there is a red flashing light at the top. Once your sample is ready to load, you'll see a green light any moment now. There it is. And then that's letting you know that your sample is ready to load. And then from there, you go back to your computer and you collect your data. Okay. So here is the unknowns proton NMR spectra. What we need you to do is jump back into Canvas now, and you're going to answer the NMR quiz, answering a few questions about the proton and carbon-13 environments and what we can tell from our spectra. So we'll give you about 5 minutes and then jump back in here and you'll have a poll waiting for you.
And we got everyone.
Okay, let's show those responses. So we've got a bit of a split here. That's all good. So let's go through our proton NMR first. And the first thing you can see is that we actually have 4 peaks shown here in our orange. So this tells us that we have 4 proton environments. The next part's really interesting. We don't have any splitting, which means they are having no neighbours near them. And we have 1 deshielded proton all on its own over here. And why do I know that it's 1? Remember the integration. So we can see here, it's a bit hard to see, but your number, it's 1, whereas you compare it to these 3 over here, and they are triple the height. So we can predict that they are methyl groups. So a bit of a prediction there. The other part that helps us here is if we went back to our molecular formula, we know that 1 plus our 3 times 3 equals our 9, gives us our 10. So that's all our protons counted for. Our carbon-13, the first part, we have 8 carbon environments shown here with our blue. And we have more deshielding at this end here. We actually have 4 carbons that are deshielded. This means that they can have nitrogens or oxygens bonded to them, pulling them up with a chemical shift. So what's our conclusion over all this? We have our molecular formula. We have our infrared data. So we know we've got carbon double bonded to carbon, carbon double bonded to oxygens. We also know we have 8 carbon environments, 4 proton environments with the ability to predict 3 methyl groups and 1 proton on its own. Now, before I continue, this one's a bit hard because the way it's positioned and the way the information you get from your data booklet with VCE, you wouldn't be expected to work out what this compound is. But that's okay, I'm going to make it a bit easier and give you 4 options. So from all our particular information we've found, I want you to work out whether you think it's adenosine, caffeine, octanoic acid, and here's my favourite one, which I'm telling you I'll probably say wrong, I'm going to start laughing, oxalic acid, now what's the last part? Dimetabolite. Okay, so we're going to chuck a poll up and see if you can work out which one you think it is. Try and stop laughing. As I said, this is a really hard compound to work it out, and you would not be expected on an exam to be like, okay, it is this. Okay, let's have a look. Oh, nice. Okay, let's go through it. So the first one we're going to cross out is C. We're looking at our molecular formula here. The first thing you will notice, there are no nitrogens. We do have the right amount of our oxygens and carbons, but there are no nitrogens here and we don't have enough hydrogens. So it can't be this one. The next one we're going to have a look at is our adenosine. And you'll see there are way too many nitrogens here. We actually have 5 in total. So it can't be this one. So that leaves us with B and D. Now the interesting part here, remember we talked about having different environments and you can have things mirrored, which gives you a multiplication of environments or divides them. So if I were to draw a line directly straight through here through our oxygen and our nitrogen rings, you'll notice that we are symmetrical, which means we would not end up with 8 carbon environments. So therefore it can't be this one. And the other part, you'll notice we don't have enough hydrogens, but the rest fits in beautifully. So the correct answer is caffeine. So well done, guys, for those who have worked it out. So what is caffeine? Why is it so important? I'm sure your teachers, especially in remote learning, will tell you it's really important right now. So you've worked out the unknown compound is caffeine. But why is it so important that we actually work out how much we are consuming? And what is caffeine in that we actually consume? These are really important questions, depending on what age you are. Now, in your Canvas shell, I have some really interesting information in there in regards to they've been reported at least 20 people worldwide that have actually died from an overdose to caffeine. They can't actually say any more have, because it's one of those weird drugs because it's found in many things. The other part, in order to OD on it, you need 10 grams minimum. So when you think about it, when people talk about like your monster drinks and all that, there are other things in there that are going to cause more havoc, like sugars, than your caffeine in the long run. So let's have a look at the functional groups. So at the top here we have our amine, and remember I was talking about with our double bonded oxygens, you have your amides at the bottom here. So we got 2 of them. Why is this so important? It's because we need to talk about whether it's a polar or a non-polar compound. So because we've got those 2 functional groups here, it makes it a non-polar compound. This is really important when we go to our HPLC, because we need to know what our mobile phase is going to be. If we're using a compound that is non-polar, we need to have a polar mobile phase to push it through. So here's an overview of our HPLC. At the start here, you have your solvent. It has to be degassed, so that means you need to remove all the air bubbles. The reason why you need no air bubbles in there is by the time it gets down to your HPLC column, you don't want any bubbles in there because it can do damage to it. So we start here, we travel down to our pump, and this is how we get our high pressure. It pumps it and pumps it so it gets higher and higher in its pressure. You then have your port here where you inject your samples, which then travels all the way down through the column, and this is where you get your separation. So the best way to think about it, if I'm a non-polar compound moving through a non-polar stationary phase, I'm going to be stopping and shaking the hands of each of the beads. If I'm a polar one, I'm going to race through. So that's why you get your separation. Then you move to your detector down the bottom here. In our case here, we have a UV detector, which then is shown in our computer as our chromatogram. If I could speak to that, it would be great. And you need to know which particular wavelength you're going to set it at. For us, caffeine's wavelength is between 260 to 270 nanometers. So now we're going to jump into our lab here. So I'm going to stop sharing. Okay, and I'm going to show you how we're going to make our standards. So just bear with us one moment. Awesome. Okay, so normally in the lab when you're making your standards from your stock solution, you would be using a volumetric flask because you're using large volumes. In our case, we are going to be using smaller volumes. So we're going to be using little containers, and we're not going to be using our large pipettes. We're going to be using our smaller pipettes. These are called micro pipettes. Can I have a show of hands as to who has actually used a micro pipette before? See if we've got any biologists in the room. Oh, yeah, wow.
About 2/3 already.
Awesome.
Most of the class has.
Awesome. So you guys would know then how we actually use them. You have your first stop, and that pulls all the air out of the barrel. And you have your second stop, generally what that means is you're going to expel that liquid. So you push it all the way down to the bottom. So I'll show it again. You got your first stop, and then I'll just turn it a bit so you can see your second stop, which is all the way down to the bottom. So when you get a liquid, what you do is you put it a tip on, you then go to your first stop, draw up the liquid, and then when you go to put it into your container of what you need, you then push it all the way down to your second stop. So what we're going to be doing is setting up our standards. We have our deionized water here, and we have our stock solution, which I'm going to be pouring into this one here. Before I get started, I need to be safe, and we need to put on our safety glasses. So we've got our stock solution and our deionized water. Now remember, in the lab, you should always label everything, because when you have clear liquids, it does get a bit confusing as to which is which. Now the last thing I haven't shown you is how to set our micropipette. So I'm going to be using this one here, and simply all you need to do is turn it around. In this particular case, I'm going to be using 1,000 microliters. Around and round it goes. Where it stops, nobody knows.
Except we know it's 1,000.
Shh. All right, then once you're in the spot, click onto there. I'm then going to get my tip on here, and I'm going to find that first stop like we did before. Going to get our liquid up. Okay. I'm going to pour it into here, and then we're going to eject. So that is our blank standard. So what we call our 0. I'm then going to be using our other micropipette to do our caffeine standard to make up our 3.7. So if you guys are in the lab, this is what you would be doing for us. You would be making up all your standards to then be put into your HPLC. So you've got your tip. Now I'm going to go and get my caffeine, go to that first stop, draw it up. Now this one is so small, it's 3.75 microliters. Okay. So you can see it's just that little dot there. It is tiny. Now, sure. You'll probably see multiple dots in there. Yeah. There we go. Okay, now what I need to do is put in our distilled water. So we set that to our 970 odd. So we get our water, first stop, draw up the liquid, and then we put it into here. Okay, now because I have my lovely assistant or lab technician, we have our ones that we prepared earlier that you can see here. And we also have our black liquid and our urine sample.
And everything is beautifully named.
So now what we need to do is move over to our HPLC and taking all our samples with us. Okay. Do you need the chair moved? So it's really important, as I was saying before, that you need to label everything so we know which particular standard you've created, and to make sure you're not crossing and doing cross-contamination. So you would have seen that I had to change my pipette tips each time because we wanted to make sure that we weren't getting any other substance in there. Okay, so we're going to come over here and have a look at our lovely KIOSC machine. So at the top here, you have your, what we call our mobile phase. It is methanol. It then comes down through here, all the way down to our pump at the bottom here. It then comes up and gets split. So this allows the degassing. Then comes up around through here to where our injection site is. Then from the back there, it comes up through the column and then back through here where it goes through the UV detector. From here, it then goes out to our computer where we get our chromatogram. The last part is the waste, and that travels all the way down here into our collector. So let's get our first sample in. So Etienne, this one here. Okay. Oh, hang on, I'm just going to stop.
Moving around. There we go.
Okay, so we have our other sample that's been prepared by Etienne. So you pull up your syringe and you can see there.
Yep.
Okay, so we're going to come into here and you inject. Now take note on here and see if you can see any droplets coming out. That simply means that we have enough injected in. You then turn this to inject, and this simply means that our machine is ready to get a baseline. So over here, you can see that we've got our mobile phase. We can see that the pump is on. You can see that it's been injected, and we can see that our UV detector is running.
Run that again now I've got the right setting.
Sure. So there's your mobile phase. The pump is on. This is where your injector is, and you've got your detector detecting this. As you can see, our baseline is coming along, and then we should see our first peak. Now, if this was our 0, we wouldn't expect a peak, and as we move through, we will end up with different peaks as we transition. Oh yeah. So the other thing is, you'll notice here, because we've been saying it's high pressure, you'll see that it's 1,631 psi. So it is high pressure. So here's one of our peaks coming through. Well, let's just change. So you can see the peak coming through, and it will simply transition off. A nice clear peak. Okay, so what we'll do is we'll go show you a video of all the different samples now, because it takes about 5 minutes to run every sample. Okay. So I'm going to jump in and share this video. Share my screen. And if anyone has any questions, please just type in. Okay, so you can see here, this is showing us what we would see for 0. Our next standard, which is our 3.7 micrograms per litre, 7.5. You can see the peak is getting higher, 11.25, 15, 18.75, and now we're going to run our 2 unknowns. So the first, oh, there's all our standards together, sorry. And now we'll run our 2 unknowns. So you've got your black liquid and then your urine sample. And here is all of them running together at once. So you can sort of start to guess what the particular concentrations we have. There we go. So I do have a YouTube clip for you to watch at a later time on Canvas. It's actually really important showing you where caffeine comes from and why we actually use it. So what I need you guys to do now, this is what I was talking about, having a graph paper. I'd like you to construct your calibration curve and then upload your image to the quiz. So that's your HPLC quiz. And then from there, I want you to read off your calibration curve, read off your unknowns. And here is the 2 areas under the graph and your retention time. So I'll give you about 5 minutes or so to draw that and then come out and draw your particular, I won't give too much away, but work out your unknown concentrations. Okay, sorry about that, guys. So what I want you to do is work out the unknown concentrations, and then from there what we need you to do is work out how much the concentration is in the urine as well. Alrighty guys, so if you haven't had a go, that's all right, just quickly have a guess. So we got 3 more to go, just quickly have a guess. Doesn't matter if you get it wrong. It's not a SAC, it's not an exam.
And the last one's a cutout, so I'm going to pull that down.
Okay, so let's have a look at your results. And you can see we've got 2 numbers that are very close. Who can tell me why we have different answers happening here? Don't be afraid, put up your hand or pop it in the chat. Why do you think we have 2 answers that look pretty strong? And this is really helpful for you guys when it comes to exams, because this would be like a sequential question. So you would have your first part, and if you got that first part wrong but carried your exact answer through, and then as you went through, ended up putting in the same parts but were showing or working out, you would still get full marks.
We've got 1 answer.
Okay.
Someone has said it depends on the calibration curve.
Well done. So it depends how you've drawn your calibration curve. So what you've drawn on your calibration curve will actually show differently for when you go to put your line across and down to work out your concentration. Now, I have been a bit evil with these 2 answers here because they are very, very close. So the answer was C. It is, or the third option, sorry, 43.11. And how you get that answer? You simply times what you've got from your reading by 3, because it's for 24 hours we've collected our urine. So this is pretty much the end for us here, guys. You've been an absolute pleasure. Now, before we let you go, I've told your teachers about a really cool app called Chemical Detectives. You can use it on your phone, you can use it on iPads, and it's really, really helpful because it can help you with practicing your spectras and reading them and analysing them. You can go from knowing what the actual compound is and working out how to work out what it is. The other part is on the post work, we have another quiz for you to practice with your exam questions, and you'll have access to this course when you've got revision for your exam. So you can come back in here and start doing some more work in your Canvas. The other part is in your post work, you have 3 unknowns to read through the spectrums to work out the answers of what they are. And your teachers will be given a PowerPoint that will be actually giving them the answers. So you may need to like pay your teacher maybe for the answers. I don't know, they might be helpful, who knows. But before we go, there's one other thing we wanted to throw up, one more poll. And the other part was that we would love for you to do our survey at the end. And we haven't put it live in our Canvas shell yet, but we will after this. We'll also put live how to work out all the different solutions. So Etienne, you've got the last poll for us?